Testing. 1, 2, 3. Ooh, that's loud. Oh my goodness, that was loud. I'm so sorry. Wow, what a start. Okay. Well, I guess that's what I get for trying to load up. Oh, I'm trying to get everything set up during these 3 minutes. So yeah, once again, just these first 3 minutes is where I try to set everything up, double check the systems, let people come in, implying that anyone's gonna come. And see where we go from there. Oh, I need to load this up. Yeah, 3 minutes may seem like a lot of time, but it's really not. Okay. What? Only a minute 45 seconds? Oh my goodness. New window. Settings. Camera. Calibrate. Please work. Whoa. Okay. There we go. There's one part. Ah, wah, 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 wah. Let's see. Mic check. Oh, I gotta load up the thing. Whoopsie daisy. Alright, music's not too loud. Oh. There we go. Okay, load this up. Oh, hey, I'm live. Okay. Oh, geez, there's still a little bit of text there. Ah, I couldn't erase all of it. All right. So, yeah, last time I think I did a writing process. Just kind of going over the whole writing process, how that could help. I was supposed to come up with a lesson plan for today. Didn't quite get to it. So we'll just wing it and see what I can come up with. Now one thing. Pre-calculus. Let's see what I can do for pre-calculus. Totally looking at a book to try to figure it out. I don't know. Should I do pre-calculus? Oh, I should put up the whole thing here. No. Tutoring live. Alright, so if anyone has any homework, any classes, any ideas for something that they might need help with at this time, I would love to hear it. You could just put in the chat. That's totally fine. If there's nothing that you want to talk about, and you just want to kind of listen to something in the background while you do your own work, that's also quite alright too. Absolutely no pressure. None at all. Tutoring live, if you want to. Man, that going over the writing process though, I think that was a real hit. Although now it's just a VOD. and now I'm just kind of live and floundering. That's fine. Alright, let's see. There's math, there's English, social studies, Well, the tricky thing about math is usually if there's like some kind of... Let's do algebra, right? It's kind of hard to make a lesson plan, I think, because everyone's going to be at like a different stage when it comes to algebra. Some people are just learning the basics with variables, right? Some people are learning the whole things about the graphs. And also Z. Whoops. And sometimes, you know, people are way into something else that I've probably forgotten by now. But it's probably important. Maybe you have a test coming up. And so maybe to some people it might seem like, oh yeah, this is baby math. I did this last year. It's super easy. Other people might think, oh, you know, this is really hard math. I don't know what I'm doing. And so just kind of thumbing through this. Ooh, absolute values and graphs. Well, there you go. Right on the money with this one. Okay. So I guess an absolute value is where you have a number that's written that is like this. And again, I don't want to be like a lecturer because I'm not a teacher, so I'm not trying to teach someone something that they might not be learning or already know or whatever. I'm trying to look at this and put it in a more practical, realistic, or hopefully visual example, one that the student can understand. And if you say, let's see, x equals -4, then it just kind of swings into being a positive. Now, maybe this is just something that you would look at and say, oh, okay, well, this is just another equation, just another thing that I have to do for school. That's fine, right? Well, what's the importance of absolute values? Why does it matter? Well, in a visual example that they like to give is, let's say, for example, you have a line, right? And you go, start right here, random point. Let's just call it 7. And you try to figure out the distance between that 7, right? And so they'd say, okay, so 4 away from that 7, this way would be 11, right? That's fine. But the funky thing about absolute values is that what if you go the opposite way, right? What if you go -4? And you end up all the way over here at 3. What this means is that, well, you end up in different numbers. You end up in different spots. But the important thing is that you are 4 away. And so the whole thing about absolute values is not necessarily about where you end up. This is kind of not important. It's more about the space in between. And so they start off with lines, but really you could kind of do that with anything, right? So let's say, for example, you are right here at 7, and you go off the grid, right? You go -4, +4, but then you go into 4 over here, 4 over there, 4 in the third dimension. All right, it doesn't matter. You can make a circle, you can make a sphere. As long as it's 4 away, that absolute value, that 4-ness, is still going to be 4 away. So that's what absolute value is in a nutshell. But how can it be used in real life, right? Why would I need to know that? Okay, sure, there's this equation for absolute value. There's this concept of something that's just 4 steps away. So what? Is that going to make me money? Probably not. But it could work for your hobbies. So say, for example, let's say you are... I don't know, what's something fun and artistic? Drawing something, stitching something, Yeah, stitches, you use grids, right? Was it not cross stitch? I forget what it's called. But there's a hobby, right, where you would have this grid system, almost like grid sheet paper, but instead of, you know, just using, whatchamacallit, numbers, you would use colors. So you do a stitch here, a stitch here, a stitch here, one there, and then you just kind of fill it out all the way around. I think I kind of messed this one up. Well, anyways, you'd go over it one by one, and in these different grids you would put colors. And these colors would eventually make a design, right? Here it looks kind of like, I guess, an eye-looking thing. There we go. And with that design, you could add other stuff. Maybe you could add like a head shape. Let me try a different one. And I'll get back to how this relates to absolute values in a minute. Let's do a head shape. Like that. And a beak. And you have a weird red crow. A red bird. Thing. I don't know my animals. I'm a tutor. I only need to know what I need to know. But, so say for example you want to make a design like that on a grid by threading some colorful yarn or string, right, on a grid system. Absolute values would actually kind of help you in a practical way. You would say, okay, so I need to figure out how to make an eyeball. And in this grid system, let's just cut it up like this. There we go. I know that I need to have 3 all the way around, right? So you get the eye in there, and then you do, let's just do green this time. 1, 2, 3. 1, 2, 3. 1, 2, 3. And here is a more, you know, practice version of absolute values, right? Where you have the grid system that you're just kind of following. I don't know, I guess like Legos. Just like this design. It just tells you, hey, you do it like this. 1, 2, 3. And then you just kind of fill in the rest, right? And then by filling in the rest with a colorful yarn, then you finally get your weird looking circle thing design, right? But not only that, let's say for example you want to make your own, right? Absolute values as a concept would kind of help you figure out how to make different things and shapes, because if you're aiming for something that has a parallel form, then you kind of know which way to go where. So, let's say for example, if only there was a grid paper system thing on here. You know that the nose is going to be here, eye is going to be over here, right? And again, this is a very poorly drawn grid. But if you work on one side, right, and you know it's exactly 1, 2, well, let me try to write it out actually. 1, 2, 3, and then 1 off to the side. Then you would know to go to the other side, right? 1, 2, 3, 1 off to the side, and you realize, oh, this eye is actually way off. It should be over here. And now you have a parallel face. This could work for art. This could work for making designs. This could work for doodling. But the idea is still the same. It's still absolute values. And what this does is this puts the maybe artistic practice of trying to aim for a parallel or matching or outward design where it's equidistant, the same on both sides, and making it into a formula. And you can kind of go backwards and forwards with this. And that's the neat thing about math, is that, and personally why I like it, is that it has a lot of parallels with art. You can kind of, if you understand one version of it, you can do the other version of it. If you understand a little bit of math, you can do a little bit more art. You get a bit of a jump start. If you understand a bit of art, then maybe you might be able to get a bit of math. Maybe. Conceptually, probably. Practically, unless you memorize the formulas, probably not. And that's the unfortunate bit, because it's all about memorizing formulas. It's not about actually putting it into practice. Let's see. So for absolute values, there's that. And of course with math, they want you to try to figure out and solve formulas. Ooh, yay. But why? Right? Let's see. Let's see if I could botch this. So we have something that I just looked in the book, where it is x plus 3 equals 9. A poorly drawn 9. Let's fix that. Alright. I solve for x. Well, that's a good question. Is there an answer sheet? Nah. Alright, let me just give it a shot. Now, it looks like it can be one of two values. Let me try to think about that. So, assuming positive, right? You have just x plus 3 equals 9. Minus 3, carried over to both sides. X equals 6. Sure, why not? And because they do the whole graph thing, boom, boom. 3, 9, good enough. Actually it's just on X, so that'd be kind of a line, wouldn't it? Yeah, there's no Y here. Let's keep it in anyways. So then, it looks like, does this make sense? X equals 6? Yeah, makes sense. 6. Now X could also be something else. Because, let's see. It could be negative as well. But I forget if the negative changes on the outside or the inside. Why would they? Oh, because I'm doing this wrong, that's why. I wrote the equation wrong and I'm doing the homework wrong and I'm skipping to another chapter. That's why it doesn't make sense. Well, let's just leave this for the side until someone actually needs help with absolute value homework. Because the funny thing is that when it comes to actual homework, it's a lot easier to kind of have, okay, the teacher said this, I need help with this. Alright, let's do it this way. Oh, this is what they meant, right? But when I'm just kind of winging it, yeah, just writing my own equations, solving my own equations, just trying to figure out the completeness of it. It's kind of boring. Let's pretend that didn't happen. But let's do something related, which is... here we go, graphing it. Okay. because I'm a bigger fan of visuals. No, that's just the same concept. Even if I said it was 4, it doesn't repeat, because it's just like, here's -4, here's +4. So then x is equal to both. Yeah, I guess that's just kind of a weirdness of it. I guess I have to use like an actual whole formula with an x and a y to kind of get a more better looking graph. Good to know. Good to know. Alright. You know what? Let's just go to something different. Let's look at inverse functions. Why are they important? Okay. I could probably do something with that. Or just functions. Sorry, I am reading while I'm trying to do this. Alright, here we go. So in math, there's also this other thing called functions. Yay. Where you have your x. And let's start simple, right? Let's not involve z, the 3D. Let's just stick with 2D. It's a way of life. X and y. And a function could be any kind of shape. It can be a squiggly. It can be like a U. Some of them can be like a pyramid. Some of them can even... Oh, geez. I don't even know how I would formulate this. Like that. That has to be annoying. So what is the importance of functions? Let's do an easy one, right? Oh, that's not it. Bam. A nice straight line. That goes from 0 onwards. And that would be... I think that'd just be the function. Is x? And x equals y? Will that just be it? No way. Let's take a look. So if we have 3 on the graph, then it becomes 3. If we have 5 on the graph, it becomes 5. Yeah, that's nice and easy. Okay, so for here, for the straight line, we have a function of x, and they might give us points and parts of it, or they might say, all right, if y equals 3, and x equals 3, then you get this. I know, it's a bit redundant, but I'm getting there. I'm getting there with something. Just give me a bit. And if x equals 5, and y equals 5, then it's this. Now the weird thing is that unless they tell us that this is the exact formula where x is equal to y, this could all be something totally different. Because what if they say, oh yeah, if x equals 4, then y equals not 4. So what would normally be is you'd think, okay, we have a straight line, right? It's 3, we have 5. It probably looks something like this. But then they throw you a curveball, and they say, well, if x equals 4, then y is not 4. You're like, maybe it's actually a curve. Maybe it kind of goes something like this. Maybe it kind of goes something like this. And then, what you initially had as f is x equals y is not there. Why is this important, though? Well, the point of functions is that there's a couple ways in which they give you the homework. They either give you the equation and tells you, alright, so this is the equation, and you need to solve for the variables and figure out how it works logically, right? So let's say, for example, here's the equation. Make sure that you do everything right and double check that everything works. Does 3 equal 3? Yes. Does 5 equal 5? Sure. Does 4 equal 4? And let's just say, for example, in this case it does, right? And I'll get back to the part where I said it doesn't. But here, the reason why they would have one blank and you have to fill out the other is so that way you can learn to follow a formula, to follow a pattern, to say, okay, if I do something here, does it always lead to here? And if I do it in proportion, is it always the same? And the best analogy I think you can apply this to is something like cooking. As weird as that might seem. If you make let's say, a cake, right? And you want to make it twice as big. Just this big old massive cake. You want to make sure that the proportions match. So then if you have 2 times the eggs, then, or if you only have 1 egg here, then in order to make it into, sorry, I'm doing this a little backwards. If you have 1 egg here, then you'll get a cake that makes of this size because it only requires 1 egg. But if you want to make it twice as big, then you have to have 2 eggs for both sides, right? And again, that seems like a very basic concept. Okay, if you want to make something twice as big, you just double it. That's fine. And this is kind of the math version of it, right? So this is the math way to say, okay, so if you have one thing and you double it, it's the same over here. If you thrice it, then it's 3 times as big. That's fine. But say, for example, you have something that's wonky like this, right? That's not a straight line. And then you have to figure out the equation because it's not x equals y. It's where maybe x equals y sometimes, in some parts, they're the same, and it works. But then if you do a little bit less or a little bit more, then your ratios are all off and you have to change it in order to be effective. And this might have to do something else too. So say, for example, if you're making a cake and you use a very certain spice. Special spice. But it's really strong, right? And for some reason, depending on the size of the thing that you make, it's not going to be the same. For example, you might think, okay, if you're going to have frosting here, you need twice as much frosting here, which would make sense, and as a visual, it might look pretty good, right? But not only is it going to be twice as wide, if you don't do it right, it might be twice as thick. Because when you do something like whisk eggs, right? Crack. Is that a whisk? That's good enough. You don't whisk it for twice as long. You actually whisk it for the same amount. So for part of the cooking recipe, yes, you may use twice as many eggs, but you don't whisk it for twice as long. Because you're still whisking that one part. Well, yeah, it's not quite the same, right? You do it for a certain amount, maybe a little bit more, but not exactly twice as much. Because, yeah, there might be twice as much eggs, but if you're whisking with these wide strokes on the bowl the first time, right, and you're able to get that egg nice and whisked, you're good, right? But if you do it the same way and you have a bigger bowl, and you do it twice as big, but then you also do it for twice as long, then you're going to get a different kind of ingredient because you're doing it for too much time. And so with things like preparing the ingredients, maybe for the ingredients themselves, you might be okay, unless you have a very overpowering flavor that you might not want to increase proportionally. Maybe you just want to kind of drizzle it or make it separately. And for the actions that you do it, right? If you're baking a cake, maybe you don't actually bake it for twice as long even though it's a bigger cake. Maybe it's just the same amount of time. Maybe it's only a little bit longer, but not proportionally exactly twice. That could be a thing. Or, you know, let's say, for example, you're making 2 small cakes, right? And they both fit in the oven. You're not going to start the oven for twice as long. That's insane. You'll use the same amount of time for the oven as you would for the other, right? Whether you're making them separately. And if you combine them together, that's fine in the oven, but you don't do the same time, because then you're just going to have burnt cake. And so with functions, this is kind of where that wibbly wobbliness comes from. Because maybe for some things it works out, but then if you do other parts of it, you got to change it up. It's not quite the same. Some parts work pretty well. Other parts, you got to really change up the formula and the whole recipe, the ingredients, but more importantly, the times in which you do things have to change. And a function can encompass all of this, right? The function could encompass the ingredients, the time, the tools, and all that stuff, all together as a function. I know, a bit weird conceptually, but that's kind of what math does, is that it puts numbers to things that we kind of practice or kind of would know or kind of do, and then it makes it into numbers, so then we could kind of also reverse engineer from numbers into this, right? So maybe not for functions specifically, well, actually for functions specifically, yeah, but also for formulas, as well as maybe things like code, where, you know, some of the time it works all the time, but other times it's totally different. I need to have things that that don't quite line up. An example would be, oh geez, do I want to go into coding? I'll save that for another time. Yeah. But going back is that when you have to figure out this math stuff, it might seem, well, this kind of sucks. Why'd I gotta learn it? Kind of, yeah. But the concept of being able to figure out a point or a part with a formula is very similar to trying to make your own recipe and your own version of someone else's formula on your own and not have it taste terrible. All this silliness and confusion is just to kind of say, you know, this is something conceptually that could help you figure out how to make your own food. Yeah. But of course, you know, that's not what you're being graded on. You're not being graded on how great of the cake you make, or what kind of ingredients that you use, or whether you're making sure that you're not, you know, you use twice the ingredients, but you're not baking for twice the time. And saying like, oh yeah, you understand that. Here, let's pass you in math. No, you still gotta learn the actual formula. So that's unfortunate. But that's how it's related. Is there any fun math stuff? Maybe. I think a very fun kind of formula is where something almost approaches infinity but doesn't quite touch it. Right? Or maybe you have a line here, and you just have some formula that goes like this, and it goes up and up and up, and it looks it's gonna be crazy, crazy, crazy. It's almost gonna touch it, but it never quite touches it, and it keeps going and going, and then for as long as you go here, positive x, it gets closer and closer to the line, but it never, ever, ever, ever touches it for like infinity. Now, why would that be fun, though? Why would that even be important? What a weird concept to have a function, a formula that almost goes all the way, but doesn't quite reach, and it just like goes. This is called, I think, parabolic, where it just shoots up, and it constantly goes up, but it just doesn't stop, or it doesn't reach a certain point. What would be a good example? What would be a good real-world example? I'm inclined to think money, but I don't want to just say money. Okay, we'll go with money. Alright, so how does this relate to money? Well, usually when it comes to money and stuff like that, people usually look at this part right here where it starts to grow. They don't usually look at the thing where it keeps going and going and going forever, but they usually look at this part where it kind of shoots up. And I think well, what's a good example? Oh boy. Stocks? Nah. Crypto? Maybe. Let's go with the big thing. Oh. Bitcoin? Gold? I think Bitcoin's a more contemporary example, but any kind of limited resource I think would work. So let's say you have money that's flexible, right? It's a wibbly wobbly money. And then let's say you have a limited resource. I don't know what Bitcoin's. I'm just gonna use gold. Why not? Sure. There we go. And let's say, for the sake of argument, there is a finite amount of gold, right? On a graph, you could say, here's gold. I think you write it at the ends of it, actually. And they wouldn't even look at this other end, but it's there. Gold. Money. Okay. And let's say there's 100 pieces of gold. Right? And money, you could say there should be a finite amount. But there kind of isn't if you have a fiat currency. It's kind of made up. So maybe you might say, oh yeah, there's only so many dollars in the world. But then, you know, that kind of goes away, right? They say, oh, we need to print more money because there's more goods and services, things are worth higher, we need to have a slight amount of, I think, inflation? And so this kind of is an imaginary border, right? There's a hard amount right here. It's only so much gold. But money, they can always print more. Although you might not like to think it that way, it can. And so over time, with the scarcity of gold, well, let's say, you know, everyone can have one piece. It doesn't matter much, right? Everyone has one. Fine. Well, what if people have 50, right? Or what if one person has 50? Then it kind of goes up. Just a wee bit. Well, what if one person has 80% of all the gold? Let's do percent. Then they'd say, okay, well, one person has 80%, so for us to get that remaining 20%, we're gonna have to pay a little bit more. And if someone has like 99%, then they're like, wow, then there's only so much gold for the rest of us. It's gonna be really expensive up here. Now mind you, I'm not looking at official charts, I'm just kind of winging it. But this is kind of the relation between a finite resource. Finite resource. And an unlimited resource. Because normally, for finite and finite resources, it would be a 1-to-1 ratio, right? If you're trading gold for copper, right? Copper might not be worth as much as gold, but there's a hard limit to both, and you could say, okay, it's kind of like this. Even if you have all the... Whoops, no, not like that. Sorry. Let's see, all the copper in the world would get you only so many gold. Probably be like... that. Yeah. Where all the copper in the world would still not get you all the copper and all the gold in the world. There's only so much. So then this would kind of be your function right here. Where you'd say, okay, just, you gotta have at least some copper, because even the tiniest bit of copper still does not equal 1 speck of gold. So you gotta have a chunk. And then maybe it's proportional, And then up to here is where you hit the limit, where even if you have all the copper in the world, it still doesn't equal gold, right? Say for example, right? I know they're both valuable resources, but this is how you would have a visual function for the value of between two items that are finite, right? But when you have something that can technically go infinite and a finite resource, then the value kind of goes into this parabolic function where you can almost have unlimited, crazy, infinity amount of this resource, but you still might not get all the thing. Now, this is important to understand as a general concept, because then you can kind of see, well, what if I have an unlimited resource and I'm trading it for a finite resource? Am I getting a good enough deal? Right, here's a, I guess, kind of a clean example of money for gold. But you can also apply this in math, of course, where there might be a specific function where it might be, oh, cool, okay, now I kind of understand that this is where no matter how much of one thing I can't get for another, right? But let's say, for example, if there's only a certain amount of ooh, I don't know. What's a good food? That's like almost extinct. I shouldn't say extinct. That they no longer make anymore. It's super special. Well, I'm just gonna make it up an example. Gold chocolate. Right? And let's say, for example, that there's gold chocolate, and it used to be a lot of it around the world. It was very cheap, but then as time went on, more and more people ate their gold chocolate. Now there's only very little left, and for the few that's left, it's exorbitantly high. It is a very high price. Now, as time goes on, and there's even less and less and less slivers of gold chocolate, then it's still going to go up and up in price over time until someone or everyone collectively deems it not worth anything or as much. Right? Maybe it might hit a few caps. They might hit a few barriers that might seem, okay, this is it. No one's ever going to pay this much anymore. But then 100 years later, it's like, oh no, it's still very valuable. It's still Fabergé eggs. You can't eat them, but you know, they only go up in price, right? Fabergé eggs. And they say, okay, this is the price of a Fabergé egg. You should not pay any more than this. Any more than that would be absolutely ridiculous, right? 100 years later. And then the price goes up. Because there's only a finite amount of it. But money and currency keeps going up. Now again, that doesn't mean that maybe you can effectively use the money that you get for your finite resource. That doesn't mean it's an equivalent exchange. Maybe $1 now will equal, I don't know, $1,000 in the future, right? So this might not be a perfect example. Maybe it might wibble wobble because the currency devalues and everything changes. Where a burger, no, not a burger. What can you get for $1? I don't know. Let's say some paper, right? And in the future, $1,000 will still get you some paper, or maybe not. Right? Maybe because the purchasing power might be different. Sorry, I'm getting to many concepts that probably aren't related to what I'm getting into here. Purchasing power is a different thing. Let's say, for example, $1 buys you a piece of paper now, and then $1,000 buys you a piece of paper in the future. So if they say, oh, okay, well, if this costs the egg $1 now, then it may or may not equal $1,000 in the future. Right? And if it technically does equal $1,000 in the future, this equation holds true, where this unlimited resource, the money, will equal the egg, right? But as far as the dollar value, it still buys one egg. One piece of paper equals one egg. $1 equals one egg here. $1,000 equals one egg and one piece of paper here. So it's still the same amount, so then it would actually function more just like as a set price that's hard. But as far as just a numerical value, just the sheer amount of money that something's worth, regardless of what you can buy with that money or how strong the dollar is, then it just goes up and up and up over time. Yeah. Anyways, so that's how an unlimited resource and a finite resource can make a parabolic function look like this. And again, that's just part of understanding the value of things. It's an important part, but it's not the only part, because again, if it still buys the same things, $1,000 in the future as a $1 now, then you are holding on to something that's not really gaining you more material wealth. It's just a number that goes up every time. And going back further, then this is why people look and study functions. Or rather, they look at data over time, and with that data, they try to reinterpret that data as a function. So again, maybe the price of a good, it might look like a scattery graph, where sometimes it's worth more, sometimes it's worth less. One time it was worth a lot, another time it might be worth nothing. And it kind of changes, and then people kind of draw lines and say, and they look at all this data, right? They say, okay, so here's how much something is worth over time. Can we turn this rough cloud of points into a function? And so that's kind of where they work backwards. Where they start having the x and y values, and then they try to figure out, well, what is the formula we're looking at? What is it? And they want to see if there's a formula, see if there's a pattern, so that way they can apply it in the future. And if you look at all these points on the graph, you could probably assume, well, at this point over here, where's the next dot going to be? Probably somewhere around right here. That seems like a safe bet. And does that make sense? Usually yes, if in a long enough time span, right? If this is, let's say, over a period of 5 minutes, yeah, no, that's, who knows, right? But if this is a period of over, like, I don't know, 50 years, then it's a pretty safe bet that things will continue to go in that pattern with that function that someone discovered by getting all the data points and making their own function to kind of figure out where things will go next. So again, simple things. Algebra, functions. People would apply them and these formulas and pattern recognition in kind of weird ways and other ways that we might not understand, like for finance and for value, and to kind of figure out, well, how can I make more money, or where's this thing going, right? And just one quick example, just to put out there, stocks. People love to do this kind of thing where they do functions, formulas, derivatives, derivatives, to kind of figure out, well, what is the value of this thing going to be in the future? Is this a good buy? It's not going to look quite like this. It'll look different. But then that's where they know where to put their money, so then they can make the most profit. And that's completely ignoring, almost completely ignoring, the practical or real application of that thing beyond just analyzing the formula and the patterns. So if they say, oh, if underwear is constantly going up and it's just, you know, underwear, that's silly. then it's a safe bet that underwear will go up forever, right? But then if they realize that, oh no, there's a big revolution where you know, something happens and there's inbuilt underwear and pants at this point in the future, and it's happening right now, and they should really pay attention to it. If you only look at the formula, then you might think, oh yeah, it's a safe bet, you know, maybe another 50 years from now, right? But then all of a sudden it craters, and you're like, what happened? It didn't follow the formula. So just be wary of that. You can apply math in this kind to a lot of stuff, but you also have to kind of pay attention when you try to apply to math outside of math and into things that are, let's say, the real world. You need to pay attention to modern events and see if there's something like underwear being built into pants, and underwear stocks would crash. A very silly and crazy example, but it's where it's one of those funny things where, you know, math isn't an exact math if you're trying to predict the future and apply it into things that aren't strictly math. But it generally works. It generally works. And I think, yeah, this is a pretty good time. Alright, I promise next week, when I stream again, that I will have a more structured and sensible lesson plan like I did with last week's writing process, which I definitely recommend anyone who wants to learn about that checks out. Not every day is a winner. That's fine. I'll just try again next week. And here's to hoping for the best. And also, yeah, I hope whoever's watching, you have a good time with this. You're entertained, you learned something, or you like the music. Yeah, that'd be nice. Alright, well, oh shoot, what am I doing? Ah, here we go. Okay, so here's my outro, and I'll see you all next week.